This is a mini lecture for showing Kirchhoff's rules. So here's a circuit out of the book, and we have a couple of batteries here, plus minus and minus plus, and then we have the resistors here, and we cannot put these two in parallel to each other in this one here because the batteries are in the way. So we have to use the alternative, which is the junction and the loop rules. Okay. The goal would be to determine what the currents are that flow through this one and this one and this one, which means we have three variables, three unknowns. So we need a system of three equations. Potentially we could come up with, I believe, let's see, 1, 2, 3, 5 equations, because we have a top loop here and we have a bottom loop. And we have the entire square as a loop, but that one would be redundant because if you put the top loop and the bottom loop together, you get the entire loop. So out of those three loops, one of them would be redundant. And then we have a junction on the left and we have a junction on the right. And I don't know why I just wrote 1 while I said actually 2 junctions. There we go. Okay, I'm going to use the top junction to begin with. I'm sorry, the top loop to begin with. But before I do that, I should label these here. This resistor here probably very likely is going to have plus minus like this. This one here is going to have minus plus. Then again, they could be turned around as well, and we would notice that later if one of our currents, for example for this one here, came out to be negative, then all it means is that I would have to turn these signs around and switch the sign in front of the current. It would be no big deal. The algebra later on will show us the correct results, as well as if we have to turn a couple of these around. Okay, well, 4 here and then a negative 1 here. I want to say that likely this is going to be a positive and this one is going to be negative. Okay, on the top loop I'm going to go up 1 volt. Then I'm going to go down the voltage across this one here, so I subtract. And for the voltage then I use Ohm's law, which is 2 ohms times the current, so this one. And this is 2 ohms, that's what that one stands for. And here I'm just going to call this I2 according to the 2 ohms. So it's easy to call these I1, I2, I3, kind of makes it nice. And so I go up 1 volt, then I go down, that's the minus, then I go around here, and then I go up, so I add a voltage respectively 1 ohm times the current, so plus 1 I1, and then I'm back here where I've started at 0, so that equals 0. Okay, bottom loop. Let's start here again. So I'm going to go up 1 volt, go down minus 2, up, down, down, minus 3, I3. And again, I'm adding actually voltages here, but due to Ohm's law, I'm able to write 2 ohms times the electric current, which is the voltage across that one. And then I go up, and I'm back to where I started, which was at 0, so plus 4.0 volts equals 0. Okay. Then I'm going to look at one of the junctions. The current flows from plus to minus, so the current flows this way. So it's going to go into the junction like this. And it flows this way, so it's also going to go into the junction like this. And then it flows plus to minus, so it flows out of the junction like that. I think we can see that if we did this on the right junction here, that of course these arrows would turn around, but basically we would have the same equation coming up with, and that makes the junction on the right hand side redundant, and we can only use one of them. So left junction, where the current is flowing in, and another current is flowing in, and that current is flowing out. So two currents that flow in equal the current that is flowing out. Okay, at this point I have three equations with three variables, I1, I2, I3, everywhere. And so I have to combine them via the elimination or substitution methods and then figure out what the individual currents are. Looks like quite some work. Well, if we recall from algebra, system of equations was quite some work. Alright, on these two top ones here, looks kind of like convenient. I could subtract from the other one. I get rid of the 1, I get rid of the negative 2i2. But unfortunately, I'm going to be left with an I1 and 3i3 when I did that, and I'm back to actually having two variables still. So even though it looks appealing to just subtract this one here, I'm not going to gain anything because I have two variables here, and as I said, if I subtract this stuff here, well, all of this subtracts as well. I'm still back to two variables. So I'm actually not going to do that. I believe what I'm going to start out with is I take this I3 and substitute it right in there, because then my second equation is going to be written in I2 and I1 and mimics, in that case, the first one here. So I reduced the first two equations to just two variables. So that's what I'm going to do. Let's see, so what I just said is I take this one here and I put it in there. Okay, I'm going to rewrite the second equation. So this is the bottom loop combined with the left junction. So I'm going to rewrite that one as 1 volt minus 2i2 minus 3 parentheses I1 plus I2, and that was my substitution, plus 4 volts, I'm going to leave out the units here, equals 0. So that's my second equation here after I substituted that one in there. Notice that this one here is in volts, this one is 2 ohms times current, so that's volts, 3 ohms times current, that's volts, plus 4 volts equals 0 volts. My loop rule is still there. So here then I'm going to combine terms. So 1 plus 4 is 5. Could have done that a while ago. Oh well. And then I have minus 2i2 minus 3i2, so I have minus 5i2 minus 3i1, and that equals 0. Okay, then I'm going to look at the one that I haven't used yet. Let me see if I can use some simple elimination with that one, and yep, maybe I can. Yep, I see it. I'll show you. Oh, I wish now that I could pull that a little bit further down, because here's what I'm going to do. I'm going to use red. I'm going to multiply this by 3 and add it to this one. So 3 times the first one, notice I get 3 minus 6I2. Why did I do that? Because I noticed that when I do that, my last one here is going to be 3I1, and then when I just add that one, I'm going to be able to eliminate the I1. And I'm kind of running out of colors here, so there we go. So add, and I'm going to have 8 minus 11I2 and here I'm going to have 0, yep, equals 0, and therefore I2 is going to equal, well, it's going to be positive 11I2, then divide by 11, so 8 over 11. Oops. And because this one here is actually volts and this one is ohms, it's volts divided by ohms, which of course is amps. And then if I really wanted to, I could write that here as 0.73 amps. Top of my head. Okay, that's one of them. That's the current I2. Now I can take that number and I can plug it in here. So yeah, in this, yeah, I just plug it in any one. I could plug it in here, I could plug it in there, I can plug it in this one here and get I1. I think I'm just going to plug it into the first one here. So let me see if I can move that down. No, not really. So I'll write it again. So the top one is going to say 1 minus 2 times 0.73 amps plus 1 I1 equals 0, and then I solve for I1. Okay, let's see what I get. First of all, I'm going to plug in actually 8 over 11. My calculator 0.7272727 and so on, and I multiply that by 2. So this part here becomes positive because it goes to the other side, so 1.45. Then I subtract 1, so I come up with 0.45, and I divide by 1, which is still 0.45, and that's my current I1. As far as the units go, let's see, this one here actually is ohms times amps, which is volts, and then to the other side, still volts. Subtract volts, still volts. Divide by, this is actually ohms, so volts divided by ohms, of course, is amps. And then I3 is going to come out to those two combined. So point, this one here, I1 plus I2. And that one is going to be 1.18 amps. So those are the three currents that are flowing through here, and notice all of them came out positive, which means my initial choices of plus and minus on here were indeed correct. I think these two here were more or less obvious, and this one here was kind of obvious too because of the 4 here being quite a bit stronger than 1. But even if one of them had been negative, all it would have taken is take the negative away and switch the corresponding plus minus around. So it wouldn't have been any big deal. Alright, we actually looked at quite a bit of algebra here, and you may recall from doing systems of equations that you can achieve the same by doing matrices. And that's what I'm going to show here. I may have to zoom out a little bit. Hold on. Let's see, zoom. There we go. Okay, that might be just enough space. Okay, I have three variables, I1, I2, I3. In my first equation, I have 1 I1, I have negative 2 I2, I have 0 for I3, and then on my right-hand side of my matrix, I would have a negative 1 once I bring it over. Remember, this is how you do matrices. On this one here, I have negative 2 I2, negative 3 I3, no I1, and I have 1 plus 4 is 5, but I have to get it to the other side, negative 5. And on this one here, I have 1 I1, 1 I2. I have to get the I3 over, so that's negative 1. And once I get that, I have 0 on the other side. So there it is. So what I did here is what you had done in college algebra before. And therefore, I'm not going to get into detail here. This one here, I'm going to transform into this kind of matrix. Where all of the ones correspond to the variables I1, I2, I3, and then I1 equals, I2 equals, I3 equals, and we'll see what we come up with. And the reason I do that is to show you an alternative method to the system of equations, and to show you that that one, of course, can be done quicker than doing all the algebra. The system of equations, so here's 3 by 4 matrix, and 1, negative 2, 0, negative 1. At this point, of course, the only thing I could do wrong is put in an incorrect entry, but then again, that could happen, so I have to be careful. And I'm going to check this one. That one looks right. If over here I have written it down correctly. That it says here negative, negative, negative. I could change this to positives, but I'm just going to leave it like this. Okay, do the math, double REF. We'll solve my entire matrix. Oops, oh, I chose REF. I meant double REF. I said so and clicked accidentally on the wrong one. So try that again. And there we go. And when you look at those, and when you look at those numbers, they're the same as what you have over here. And in fact, I'm going to make it easy on myself. Nope, there it is. That's the one. And I paste it in there. There it is. And then, of course, these are amps, amps, and amps, and just the same numbers that I calculated with the system of equations. And then I do want to show this using the applet. So Okay, one resistor, and I put the ammeter right next to it, and another resistor, and the battery, and that one should be correct here, and this one is 1 volt. And then another battery, and this should be turned around, and that's 4 volts. Ammeter, and here we go, and let's see, this one is 3, 2, and 1. And connect with the wires. Oh yeah, show values. There we go. Alright. Combine them all. And I think this is going to be actually really quick. There, we're done. 0.48 amps. I'm sorry, 0.45 amps, 0.73 amps, 1.18 amps as calculated with the system of equations respectively. The matrix.